Okay, we have a couple things to do to finish up this chapter. One of them is to talk about the effect of how we choose our system on how we write the energy equations. Okay, we've seen that we have to be careful in choosing systems because because once we've decided what's the system and what's the surroundings, we have to stick to that or we do our bookkeeping wrong. And we chose in this case as our system a closed system, both of the blocks, and then there was no input from the surroundings. If we'd chosen one block as the system and the other as the surroundings, then we would have had to write our equations differently. So, and we chose a closed system. A different choice would have been an open system. And so even in a very simple, and one of the key pieces is this whole potential energy thing. If you choose one object as a system, then you don't have potential energy terms. You often have work by the surroundings. But if you choose two objects as a system, there may be no work by the surroundings, but there are changes in potential energy. You can do it either way. You have to stick to it. Sometimes one choice is just a lot more informative and convenient than another. And we'll discuss a simple example now, and then in one of your homework assignments, you're asked actually to study a sort of a much more complex example in the textbook that has a woman, a barbell, and the earth, and goes through several different choices of system. And you can see that what comes out of it, you're actually able to calculate different quantities. But let's just consider a simple situation here just to make the point, which is here's the earth, here's a ball. It starts at some height, goes up a certain distance, and comes to a stop. Okay? Now, there are two obvious possible choices of system. We could choose the ball as a system, or we could choose the earth plus the ball as a system. In each case, we're going to use the energy principle, but or we can write it out this way: E final equals E initial plus W plus Q. We're always going to have to. So the question is Q always going to be included in the energy principle? We are going to need to ask ourselves if Q is zero or non-zero. There'll be plenty of situations where we can decide Q is zero, in part because things may happen quickly. So that if it happens quickly enough that there isn't time for much energy transfer due to temperature differences, we can say Q is approximately zero. There certainly are going to be situations where it's not zero, though, and we have to worry about it. So we're going to have to ask ourselves, can we say it's zero or not? So just as an example, here's the situation. The ball goes up, comes to a stop. Obviously, it started from some non-zero speed. And so the question is, which of these equations, and now in this equation we are assuming Q is zero, would we write to describe the system of the ball alone, not the ball plus the earth? Okay, so we better write it out. So this is why it's actually important to talk about this, because you can make mistakes if you're not careful. So the system is the ball, and what kind of energy can the ball have? Rest energy, but that doesn't change. Kinetic energy. It could have internal energy. It could get hot, but we're going to make the assumption that during this time, there's the ball and the atmosphere were at the same temperature. Okay, so we want to start with E final equals E initial plus work done by the surroundings. What's in the surroundings? The Earth. Ah. Okay, so let's take the next step. So the ball has some initial kinetic energy, right? Because it's got some initial speed, so it's a half m ball v initial squared. And what about its final kinetic energy? 0. Okay. And is there potential energy in this system? No, why not? Because there's only one object in the system. The Earth is outside. And remember, you have to have pairs of interacting objects inside the system. But we do have work done by the surroundings. And what is the work done by the Earth? Okay, let's make sure we're right. So this is delta y. And the force by the Earth is down. And so the force exerted by the Earth is opposite to the displacement, which means that it's going to be doing negative work, isn't it? So we've got a negative mg, and what did it move? A distance h? Okay. So that looks like equation 1. Equation 4 looks like you were sloppy about the sign of work, which is always bad because you're going to have the ball going faster after it's gone up 3 feet. And so to be careful, you really might want to write things as a vector. So we have 0 minus mg, 0 times delta y, 0 plus h, 0. We get this negative work. What about equation 2? What would that be for? What does that correspond to? That sounds like the Earth plus the ball, doesn't it? Because if we have Earth plus ball, then we would have K final plus U final is K initial plus U initial plus the work done by the surroundings. And in this case, the work by the surroundings is going to be 0 because there's not much of interest in the surroundings anymore since the Earth is in the system. And so that's 0, but this is going to be mg times h plus whatever y initial was, and that's going to be a half mv initial squared plus mg times whatever y initial was. And so simplifying, we get a change in potential energy is a half mv initial squared plus 0. Now you should get the same answer, but if you mix up the two, you're not going to. So that's the message. Let me just advertise for the woman, the Earth, and the barbell. So woman lifts a barbell starting at rest, and exerts an upward force on it until at some point, at the ending point, she's still pushing up, and it's now going up with some speed v. So the barbell can have kinetic energy, and depending on how you choose the system, there's potential energy. But the thing that's really different here is that there's internal energy of the woman. In fact, does her internal energy change during this process? It does, doesn't it? Because how did she get energy to do work on the barbell? She's converting chemical energy, isn't she? And she might be getting hot, too. So this is a complex system. And okay, so you should read that and study it.